When you are attempting to master advanced fields like neural networks or fluid dynamics, there is a specific type of friction you eventually encounter. The progression of the topic remains clear, but your ability to move through the calculations begins to seize up. In many cases, the roadblock isn't the software or the modern high-level concepts. Instead, the friction often stems from a lack of fluency in the underlying mathematical logic that supports those systems. Modern textbooks often bypass this depth. Contemporary curricula frequently prioritize approachability, using colorful visual aids and providing formulas as prepackaged tools. This helps you reach an answer quickly, but it often skips the rigorous proofs required to understand why that answer is true. There is a historically proven alternative. For much of the 20th century, engineers and scientists were trained using an educational philosophy that removed these distractions, focusing instead on the uncompromising derivation of every mathematical rule. Returning to these classical mathematical texts allows you to rebuild that foundation, replacing memorized shortcuts with a granular understanding of how systems are actually constructed. This repository contains over 100 of these classical works, focusing on Soviet-era mathematics, physics, and probability texts. To make this archive navigable, we organized the texts into 3 distinct domains: Foundations, Advanced Systems, and Applied Sciences. These books are built on a specific instructional cycle: define the concept, prove the rule, apply it, and practice until the logic becomes second nature. However, these books present a high barrier to entry. They utilize historical notation and demand a significant investment of time. Choosing a text at random often leads to unnecessary frustration. The goal is to identify a highly optimized path through the archive, one that addresses your specific technical gaps without requiring you to read every volume. Correcting your mathematical bottleneck requires matching the text to your current discipline, ensuring your cognitive effort is spent where it will have the most impact. For those needing a complete reset, A.P. Kiselev's arithmetic and algebra texts are the starting point. These books were the official training tools for generations of scientists, with over 100 million copies printed over the last century. This path is designed for educators, parents, or professionals who need to rebuild their structural logic from the ground up. This comparison shows the shift. Modern books provide prepackaged formulas, while Kiselev derives rules from real-world problems. Everything is earned through proof. The curriculum moves methodically, starting with monomials, progressing to logarithms and complex numbers. The trade-off is the complete removal of modern conveniences. You will not find color-coded callouts, pro tips, or simplified summaries to speed up the process. This method requires patience. Your initial progress will be significantly slower than it would be with a modern test prep course or a digital tutorial. The result of this deliberate pace is a durable level of mathematical intuition. Because you have derived the system yourself, the logic becomes a permanent part of your analytical toolkit. For foundational mastery, the high initial friction of the Kiselev method is the most reliable way to ensure you actually retain what you learn. If you are working in AI, the bottleneck is often probability theory. This requires a transition to the advanced systems path. This route focuses on the foundational work of A. Markov, the father of Markov chains, and the probability texts of A.N. Kolmogorov. These 1900-era texts provide the theoretical bedrock for stochastic processes. This is the exact mathematical architecture that allows modern large language models to function. However, these books offer pure theory. They do not contain software integrations, Python examples, or any reference to modern data science. You are responsible for the bridge. It requires significant effort to map this historical notation onto the frameworks and libraries you use in your daily work. This theoretical deep dive separates engineers who merely use code libraries from those who understand the probabilistic mechanics driving the algorithm. The final path addresses applied sciences, featuring the notoriously difficult books by authors like Irodov and Gontmacher. These books provide very little explanatory text. They assume you already possess mathematical fluency, and instead focus on presenting problems that have no obvious or immediate solution. The goal is to force you to construct your own mental models. This style is designed to build a culture of persistence and rigorous problem-solving. This path will be frustrating for anyone who relies on quick, step-by-step solutions. There is no hand-holding provided. This approach is for those who prioritize an intuitive, internal grasp of mechanics over the ease of the learning process. We have evaluated the archive. Now we can assign specific starting points based on your current goals. This decision matrix routes you based on your objective: foundational rebuilding, deep AI theory, or immediate practical application. Beginners and educators seeking a reset should follow the Foundations branch to Kiselev's Algebra and Arithmetic. AI practitioners who want to understand the core mechanics of their models should move down the advanced theory path to the Markov and Kolmogorov probability bundle. If your time is limited and you need to deploy tools immediately, you should bypass the classical archive and look toward modern texts like Diesenroth's Mathematics for Machine Learning. Classical texts require a time investment that is only profitable if you can afford to translate the theory into modern tools. For the purely time constraint, the return on that investment may be negative. There is no universally best book in this collection. The value is determined entirely by your available time and the specific technical gap you are trying to close. Every classical text mentioned here shares one unifying trait: the deliberate use of cognitive friction. Mathematical mastery is not a passive experience. The depth of your understanding is tied directly to the quality of the logical struggle required to reach it. If you choose one of these paths, you must be willing to put away modern shortcuts and accept the effort these texts demand. In a landscape where most rely on automated shortcuts, the ability to reconstruct a system's logic from first principles remains a rare and practical skill.